homework? I think we probably will be allocating some time to answer questions about homework. Or would you prefer to do that now? Okay, so questions about the homework. Anyone has any questions? Should I bring up the homework so we can sort of talk about it? Okay, so any questions about the homework? Who has finished already? Anyone? No one? So people all good? All good. Okay. So I think what I will do is that it'll be great for you to get started with your homework. And if you do have any questions, maybe we can also do the same question and answer next week when we meet, because I think a lot of you still probably haven't got a chance to have actually a much deeper thinking about what the homework is about. So maybe there's not that many questions that you want to ask, but perhaps it's not a good idea to wait for the absolute last week, and because by then it might be too late. So just maybe what I will do is that I think I'll get people to start thinking about how you wanted to tackle that particular problem, okay? And then once you sort of have some solid ideas about this particular homework, and you probably have more questions that you want to ask. Okay, so I will leave that till next week. I know it's still 20 days left, but 20 days can go really fast. I estimate like if you spend 1 day on this homework, you'll be able to finish it. But sometimes just to get things started, that is of a challenge to a lot of people. Okay, so that's fine. We will come back to this next week. Today's lecture is probably the most abstract of the entire subject. We're going to talk about machine learning theory. Okay, so when we talk about theory, things are becoming very abstract. So don't treat today's lecture as like because you know how in most cases the lectures kind of gets harder and harder and harder, right? So today's topic isn't going to be harder than any other topics, and it's very theoretical. So, and that's why I was only prepared to talk to you about it for the first 6 pages. And I'm not going to ask you to learn about the things in the subsequent pages. These are for PhD students, not for this particular class. So I am just gonna finishing off in 6 pages only. So we will spend 3 hours to talk about 6 pages. And if we have time left, I probably will go back to the neural network notes for you to ask me questions on that as well, because that's very, very important. Yeah, so let's just get started. Who actually has some knowledge about learning theory? Okay, probably not. So maybe I will get started with 2 of the very important quantity, which you will see again and again and again in the literature. One's called empirical risk. Okay, empirical risk. So just have a look at this. Imagine that we are building a binary classification. Okay, we are building a binary classification. So yi can actually be what? 0 and 1. Okay, y can only be 0 and 1, and just binary classification. So what does this mean? Like what does this mean? Just have a look at this. So that is the average the average times number of times that the proportionality of the chances that you're gonna predict something which is different to your true label. Okay, right. So that's called the empirical risk, right? So if you look at this, so what does this symbol mean? So if you have true, that's going to return you 1. So you have you seen a true indicator function before? Maybe what I will do, I'll change the notes. I'll put this definition in. I just thought that you probably know that before. So, you know, if it's just x, then x equal to true, 0 otherwise. Okay. So if you look at this, if you predict it right, you get 0. So there is no risk. There's no loss. Okay. And if you're predicting something which is different to the label, you are actually going to have a loss of 1. Okay. So you're going to have a loss of 1. Is that clear? Okay. So if you're predicting something that's wrong, so let me just, for example, I've got three data: x1, x2, and x3. Okay. I got y1. Y1 is equal to 1, y2 equal to 0, y3 equal to 1. And just imagine that I'm running some kind of hypothesis. Hypothesis is just another way of saying it's a model. So when you are doing machine learning application, you call it a model, right? Typically, you're going to call this like f theta or something like that, right? Neural network with a parameter theta. But if you are actually working on machine learning theory, then you will use the letter H because that is another word for a model, which we call hypothesis. Okay. So like a neural network is a hypothesis, right? And then you will have the concept of having hypothesis sets. So if I tell you that is, you got to solve this problem using neural network, right? With a softmax as a last layer, and that's your hypothesis set. You don't know which parameters to use. So that's all the parameters within that neural network setting that you can choose from. But which parameter would you use, right? So that's an element within your hypothesis set. Is that clear? Okay, that's clear, right? So let me just sort of say it's more, so just, you know how last week we talked about neural networks, all right? We have this, okay? If I actually wanted you to do a linear regression using the neural network as a way of doing data projection, then you have another parameter called, I shouldn't call it W, I call it like V, okay, V transpose, right? So if I can define this as my hypothesis, right? This is my hypothesis. So I'm going to say F, I'm running out of space, but I'm just going to say, this is my hypothesis, right? Of X, okay? But this hypothesis will take 2 parameters. One is V and the other one is W, right? But as you know that by changing the values of V and W, you are actually going to get a different hypothesis. Now, the set of hypotheses you're going to have, we're going to denote this by like a curly H. Okay, so that's the set of hypotheses you can possibly have, right? And so you need to find a particular hypothesis within the set of hypotheses that you're allowed to have. That's the goal of learning, right? That's the goal of machine learning. Okay, so coming back to this particular problem. Now, we knew that this particular hypothesis is actually going to producing something either 0 or 1, okay, 0 or 1. Now, if it matches with this, y, so for example, I'm just going to say that's equal to 1, and this is equal to 1, and this also equal to 1. Now, you know this is right, so it will receive 0 penalty, 0 loss. You know this is wrong, so it will receive penalty of 1. And this is also right, it will receive penalty of 0. Okay, so can anyone sort of tell me what is the empirical risk for this set of data? So when I'm giving a set S, with x1, y1, x2, y2, x3, y3, and and in this kind of form. So what would be the empirical loss for this particular hypothesis H? It should be in this particular example. What do you get? You get 1/3, right? You get 1/3. Okay, because there's only one. This will attract a loss because it's different, right? Different, you get loss of 1, and there are 3 of them. So 1 divided by 3 is 1/3. Okay, so empirical loss is 1/3. Okay, is that clear? All right, so nothing, by the way, there's a lot of equation here, but the equations are not hard, right? They're just simple probabilities. And if you study your first year maths, you'll be able to understand those things. But the concept is slightly more complex than the actual formula. So you'll understand about empirical risk, right? Okay, now we come to another thing called the expected risk. So what do I mean by expected risk? Is, okay, why are we getting this kind of so maybe I'll give you like a number like 0.3. So I shouldn't call it 0. So this is usually a vector, right? This is usually a vector. So I'm gonna be like 5. This is 6. This is 7. Okay. So you are actually gonna get your sets is is like 5, 1, 6, 0, and 7, 1. Okay, so this is the set of data you got given. Now, why do you get that particular set? Why not some other sets? Okay, so where are your data coming from? Your data or your sample data is actually come from a distribution of all the possible data that you can have in the world, right? So that's the underlying assumption. The underlying assumption of the training data you're going to have to train your model with, each one of these data is actually an IID draw from the distribution describing every piece of data in the world, okay? So let's assume there is an underlying, so let me just get rid of that. So let's assume there is an underlying distribution. Like there's an underlying distribution of every bit of our images in the world, right? And and together, so this distribution is not just about the data itself, and also with its label. Okay, the data and the label pair. So this is a distribution, right? This is distribution. That distribution is about the data, right? And the label pair, okay? The data and the label pair. They're coming in pairs, right? So the data and the label pair. Now, all your training data is assumed to be a identical and independent samples from this distribution, which we do not know. We just assume that there is one, okay? Right, so just imagine you are performing a classification on your MNet data, or on your ImageNet data, or on your AlexNet data, or on your MS Coco data. So you kind of assuming these are just random samples from every bit of data that's available in the world, okay? So now imagine that you have something like that, and you take every pair of possible data with different probability, of course, and you are actually going to computing the loss, okay? You are actually going to computing the loss. You're going to compute the average loss, okay? And that's going to give you something called the expected risk, okay? Can I ask you to think about why these two are the same? This and that. Why these two are the same? Obviously, they have to be the same. Otherwise, right, well, otherwise that formula doesn't work. Why do they have to be the same? So what's this? Like, what's this in relation with that? I think this particular formulation may look a little bit strange initially, but if I do ask you to say, let's actually take a sample, just take one sample from, say, a distribution that you already know very well, like a Gaussian distribution, right? Just imagine you take a sample from it, right? And then you are trying to computing the expectation of the sample. What would that give you? So if you take a sample from a distribution, right? And you take another sample from the same distribution, you take another sample from the distribution, start calculating the expectation of that sample, of that random variable. What do you get? You're gonna get mu, right? Yeah, okay. So again, you can do the same thing. You can say, I wanted to draw, you know, a set S from, this is where xi iid from your Gaussian distribution, right? You do that. And then you will start computing the expectation of when these sets, are actually drawn in this fashion, right? And then you want to compute 1 over n. Sorry, maybe I will use the symbols a little better. 1 over s, okay? Then you have a summation, right, of s. So if you actually do that, and what do you get? What's the expectation of that? So if you're actually drawing, like m ID samples, and you calculate the average, and then you draw another m samples, calculate the average. Then you draw another one, set of m samples, calculate the average. Then you compute the expected value of those samples, those sample averages. What do you get? What are you going to get? You're still going to get mu, right? You're still going to get mu. Yeah. So by doing this, that's just that, right? And by doing this, this is just that. Okay. So this is like take one sample. This is where you let the number of samples equal to 1. And this is where you let the number of samples to be an arbitrary number. But the average are exactly the same. Okay. So yeah, so this is called the expected risk. And yes, you can see that the expected risk is the average of all your empirical risks. Okay. So these are the empirical risks. Usually I will have a, like a hat on it. And this is the expected risk. Okay. All right. So is that clear? And if it's not clear, please do ask me. I wanted to make sure you are clear with this until we keep on going. By the way, there's only 6 slides in today's lecture, right? And I'm intend to go through these 6 slides. Shouldn't be a challenge. So far, so good. Okay. So now I'm going to show you the big picture. And when I mean by picture, I literally mean the big picture because I actually show this in a very large sort of format. And sort of let's have a look at this, right? Let's have a look at this. Let's not worry about the other ones later. And in fact, I am going to ask you to look at this thing first. What does this mean? So that's the intersection, right, of this particular event. And that's the intersection of this event and that event. So can people tell me, what does this thing say? Like if you just look at, I'm gonna enlarge it even further. So what does this thing say? It says for a particular hypothesis H, like a neural network with certain parameter value, the empirical risk is 0 and the expected risk is greater than epsilon. So what does that say about H? Using the language that you are more familiar with. I mean, using the machine learning language that you're more familiar with. What does that say about age? Only one word. Age. Huh? Is good. That's usually bad, right? The empirical risk 0, expect the risk greater than epsilon. I mean, greater than epsilon is usually bad. You don't want that. So what does that say about H? Only one word. Anyone wants to have a go at? Overfitting, thank you. So it overfits, right? So that particular H overfits. When something has 0 empirical value, it means that it has 0 what? Training error. Okay? When something, by the way, what's this? What is this? So if this is a training error, and what's this? That's the testing error. I mean, it's not the kind of testing error that you are more familiar with. Like what you will do is that you are getting a, so can I take this out? People are familiar with this. So if you are giving a set of data, say, you know, this is like X1, Y1, X2, Y2, X3, Y3, and all the way to Xn minus 1, Yn minus 1, Xn, and Yn. How do you actually build your model and verify the accuracy of your model? You will do the split, right? You're gonna split it into. By the way, you don't usually split it, like in some kind of order, because the data may have certain structure that you don't want to do that. You probably want to randomly split the data. So you're going to call this as your training, right? And call this as your testing, yes? And you will pretend that you do not know the true value, the ground truth of your testing data. And then you will use this thing. You will use your training data to actually build the model, theta. And then you will verify how accurate this theta is by using this to do the prediction, right? And then you will compare with your ground truths to see how accurate they are. So you have all seen that before, right? That's how you build a model, right? That's how you build a model. If you haven't seen that, maybe it's worthwhile to thinking about this, and it's not very hard. You know, you're given a set of data, you use a part of your data to build your model, and then you learn the model from the theta, and then you substitute the data in, and then you pretended that you do not know these labels, right? And then use it for prediction, then you compare with your ground truth. Then you will know how accurate your model is, yeah? And you will need to do that multiple times. It's called multiple fold cross validation, right? If you do that 10 times, if you do that split, training and testing split 10 times, you're gonna get, you will call them 10-fold cross validation. Can I ask, why do you need to do that 10 times, multiple times? So why isn't once enough? Yes, any suggestions? Physics. Right, maybe give me a little bit more concrete. Think about an extreme scenario. Maybe I'll show you. Right. So think about one extreme scenario where you have data looks like this. Okay, your positive data it's in here, and your negative data that's in here. Okay. So you kind of build your model, like this. All right, so you will get 0 training error, which is fine. And I'm just gonna erase this. But as you know, data is not perfect, right? So sometimes you can have a few of, what do we call this? What's the name of this data? This is called outliers, right? It's called outliers. Outliers. And by the way, if they are called outliers, then the good data is called the inliers, okay? So these are means that the data that go with the general pattern. So these are the inliers. The data go against the general pattern. They are called outliers. Now, let me ask you, imagine that you have the data looks like that. Where is your decision boundary? Imagine you have a few outliers. Where should your decision boundary be? I believe you will say still the same as before. Yes. Okay. So that's where the decision boundary should be. I mean, you know, in the presence of few outliers, you shouldn't actually change the way how you actually classify your data. Now, watch this. What if you have selected this to be your testing? I mean, by the way, outliers, there's only a few. Usually testing data is small as well. What if you select this as a testing data? Where is your learn decision boundary? Where's your parameter? It's still this green line, yeah? Still this green line here. But what does it say about your testing error? 0, right? You have built a perfectly good model because you have, in the extreme case, you have selected all your inliers to be your training data. So that allows you to build a model which is perfect. That's great. That's correct, right? But because your testing data are all your outlier data, right? It actually makes it says that your accuracy, the model you have built, like that green line there, actually has 0 accuracy. Is that good? It's not good, right? How can you prevent this? Do that multiple times. Do it multiple times. So the probability of selecting, so let's summarize. The probability of selecting your training and testing from 2 different distributions will be minimized. Remember, inliers have its own distribution. Outliers have another distribution, right? So therefore, you want to minimize the chance that you select your inlier data from one distribution, outlier data from another distribution. And the way to prevent that is to do that multiple times. And that's why we need to do using can-fold cross-validation. Okay, so that's good. So we all, and by the way, this can be regarded as testing error, yeah? But this is not this is regarded as a training error. But it cannot be regarded as the testing error I just talked about it. Because the testing error that you are more familiar with are actually some samples that's drawn from your data distribution. The testing error we talk about here are every bit of data that's available in the world. Yes, so this is not the testing data. Sometimes I love to write, expected risk / testing error, but that's not the true testing error. That's not the testing error that you are familiar with. So it doesn't come in samples. It means pretty much you got to test every single data you have not seen before. Okay. Is that okay? Right. Yeah. Okay. Any questions? So what do you want to do? Like, what do you want to do? You want to find the probability, right? So this means overfit, right? So this means H overfit. H overfits. So can anyone tell me about this in English? What does it say? The probability of some hypothesis overfit, right? the probability of at least one hypothesis overfit, right? I mean, that's what this thing says, right? The probability of at least one hypothesis overfit. Okay? So we like it to be, do you like the probability to be big or small? Small, right? So therefore, you would like this probability to be bounded. You like that to be bounded. You want to have an upper bound for that. And that's where PAC learning actually tells you. You're going to be upper bounded by this, okay? So what if the probability of at least some hypothesis overfits to be upper bounded by this quantity? If you change the notations around, you're going to get something like this, okay? Now, M is the number of data points, okay? M is the number of data points. And this two lines are the cardinality of hypothesis set. So which means that the number of possible hypotheses you can possibly have. I can ask you if you have a neural network, what's your cardinality of a neural network? How many different neural networks can you have if you just have one layer of neural network? How many? What's the parameter for a neural network? Is W, remember? So how many different hypotheses that exist for a neural network of one layer? Infinite, because that matrix you can put any values in, right? You can put 5, 5.5, 5.6, and any values in. You can go all the way to 100 digits if you like. So in neural network, this is actually infinite. Just out of curiosity, there are ways to actually make an infinite hypothesis to a finite hypothesis. This is an idea called epsilon coverage. So just imagine that you are in a room. You know, this is like you have infinite division of spaces, right? But what you can do is that you can fill up this room with balloon of certain radius. And the number of balloons that would take to fill up this room is finite. Okay? And once you convert an infinite space into a finite, or I should say hypothesis, once you convert something from the infinite number of hypotheses into the finite number of hypotheses, then you can actually use a lot of interesting theorems in learning theory. Right? So anyway, that particular technique is called the chaining. And there's something called Dudley theorem if you're ever interested in reading about learning theory. So I've actually written a lot of notes on this area because it's my primary line of research. So if you are interested, have a read about my learning theory notes. You know, I will explain them in detail. But of course, I'm not gonna put that in for this particular subject because it's actually way too theoretical. Okay, so all right, but you get the idea, right? And so if I actually bring M to this, in order to satisfy this equation here, I can rewrite this in this form, right? I can rewrite this in this form. So which means that if I fix epsilon, if I fix delta, I can actually compute what the M should be, right? What's the lower bound of M? So in order to have at least that many number of training data, I can ensure that this and this guy stay low. Okay? These two guys stay low. Now, can I just ask, what do I mean by epsilon stay low? What does epsilon try to tell you? What does epsilon try to tell you? Epsilon is the threshold to decide whether an H overfits or not. Yes? So remember, this is the criteria to decide that H overfits, right? If the expected loss is greater than epsilon, it overfits. If it's less than or equal to epsilon, it doesn't overfit. So epsilon is the criteria. So if epsilon is small, it just means the criteria is very stringent, right? Very strict. For example, if the testing error is greater than 0.001, which is a very funny number, you should allow that. And you kind of say, oh no, this overfits. And therefore, if it happens, you're going to choose a very large n. Yeah? By the way, can I just ask, what if m is infinite? If you have infinite training data, which means that you are able to get every single piece of data in the world, right? What happens? What's going to happen to the quantities you have seen in this lecture notes? If you have infinite number of training data, your expected, I mean, in generally speaking, right? This expected risk is equal to your empirical risk. I mean, not necessarily has to be zero, but they are the same. Okay, the average of that is the same as. Oh, the average of that is always that, but that and that will equate. Okay, so when this and that equates, not only the average are the same, the variance is zero. Okay, so they are exactly the same. So the empirical loss becomes your expected loss. And that can be reflected in here, right? If you let this guy become zero, right? And this will become infinite. Okay. And yeah. Cool. So that's it. Any questions? I kind of have a bit of wording sort of written in here. So yeah, this is for you to have a think about it. All right. So just to reinforce your understanding a little bit further, I am using another alternative expression to expressing that. So when I'm saying something about this, the probability, so I know this is a very long equation, but just sort of treating this as like some kind of event, right? Some kind of event. So the probability of some kind of event is greater than this, right? So can I just ask, maybe this is too long, but I'm just gonna ask, right? So probability of x less than epsilon greater or equal to 1 minus that. What's the alternative way of writing this? So then you will say this whole thing can be written as x. Right? Maybe I'll using a different symbol. I'll call it y so that it's not be confused. So I'm just gonna call this y. Okay. So if I say a random variable, which is the probability of random variable is greater than 1 minus epsilon. So another way to say there are at least 1 minus delta. I keep on saying this epsilon, right? This is delta. So there's at least 1 minus delta probability that this is less than that, right? So another way of writing this is that to say at least 1 minus delta probability y is less than that. Okay. These are all the, these are all you if you're reading a learning theory paper, you will see these two type of writing, and this is even more popular. And sometimes people will say something like that. They're going to say something like with high probability. Or sometimes people just say WHP. These are all meant the same thing. Okay. So, but can I just ask, what's the alternative way of expressing this? Yes. So the probability of y greater than epsilon is less than delta, okay? So I'm gonna say in words with a most delta probability, y is greater than that, okay? So I mean, one easy way to remember that is these signs are different. These signs are different. But can these signs be the same? Yes, it also happens. So if that happens, it's called an anti-concentration probability. By the way, this kind of probabilities, does anyone know what the name of these probabilities are? These are called concentration inequality. So the reason why they call it concentration inequality, this is a concentration, right? Something greater than something, right? The probability of something greater, so it's not probability of something equal to. I mean, this is what you are used to, right? The probability of x equal to 3, or the probability of x equal to something. And in learning theory, it's usually the probability of something greater than, or something that's less than, right? So that's called concentration inequality. Yeah, concentration inequality, right? Concentration inequality. Again, if you are interested in reading this further, I have written a very, very lengthy tutorial about the 6 different concentration inequality that people are using in learning theory. You also know one, at least. Tell me one concentration inequality you have studied before. Markov, right? Markov inequality. By the way, every single concentration inequality are all derived from Markov inequality. Okay, every single one of them, like Chebyshev, like Halfting inequality, which I'm going to show you today. I'm not going to show you, but I'm not going to show you its proof. The proof is very, very long. Yes, I need to show you what is Markov lemma before we show you Markov inequality. But every single concentration inequality is a product of Markov inequality. Okay. So that's good. You are doing very well. We have gone through the first page. So there's 6 pages to go. That's fine. We will speed up a little bit in the video class. So we have 4 minutes and let's just keep on going. All right. So do you agree with me that they are meant exactly the same thing? These 3 statements meant exactly the same thing. So don't worry too much about this notation. Just so SA. Let's just sort of thinking that as just some kind of hypothesis H, right? Think that as a particular hypothesis H. So this is called empirical minimizer. Empirical minimizer. Sorry, empirical risk minimizer. Sorry, I keep on forgetting the name. So this is called the empirical risk minimizer. And why do they? So what are these 3 elements? So this is the training data sets, right? The S as your data, your set of data set S. And A is an algorithm. So, and using this algorithm, performing on this kind of sets, you derive this particular H, okay? So it's like, this is like a gradient descent, like a gradient descent. And this is your data. And this is, the neural network that you have just discovered, the neural network parameter you have just discovered. Okay, so just treating that as a particular, like a particular hypothesis. Okay, all right. So can you sort of tell that this and this are exactly the same? Yeah, okay. So why? So you all know that the probability of an event, right, is equal to the expectation of an indicator of an event, right? Okay. I mean, this is something that you have studied when you study your first year probability. Okay. And so these are exactly the same. And also the reason why they are the same is because I just talked about that before. They are the same. Yeah, these are the same. Okay. So the lastly, why do we call them PAC learnable? Something that's PAC learnable is because what does PAC mean? PAC means probably, approximately accurate. I know it's a very, very strange name, right? It's probably, approximately accurate. So what does that mean? It means that with at least this much probability, so probably, okay, probably. And so you remember, like, if we look at this equation here, with at least this much probability, the expected risk is less than that. So expected risk less than that is approximately accurate. Okay, so it just means that when you train something and you apply them in future unseen data, and that's probably going to be accurate, right? And with at least this pretty much probability, it's going to be approximately accurate. Okay, is that clear? All right, now it's a good time to have a break, and we will, after the break. By the way, when I say 6 slides, there's only 5.5, so we are right on time to finish it up. And don't worry too much. This is the first and last time you will see about learning theory in this particular class. But hopefully, that's going to build you with some interest in pursuing future studies in this very exciting topics of learning theory. Okay, so I'm going to take a break and get some